Hello there and welcome. Tonight, we're going to journey to the heart of our solar system, to the star that has warmed Earth for billions of years, the Sun. To most of us, it appears as a bright disk in the sky, rising each morning and setting each evening. But in reality, it is an enormous sphere of roiling plasma, burning with the light of 400 billion watts. Its surface churns with magnetic storms. Its core crushes matter under unimaginable pressure. And through it all, the sun shines steadily, quietly sustaining every living thing we know. Tonight, we'll explore 100 facts about this magnificent star. Allow your breathing to slow, let your thoughts drift, and join me as we discover the wonders of the sun, one gentle fact at a time. The sun is not simply a bright object in our sky. It is a star, just like the countless points of light you see scattered across the night. The difference is distance. While other stars lie trillions upon trillions of kilometers away, the sun sits at our cosmic doorstep, close enough to warm our planet and illuminate our days. It is a massive sphere of hot plasma, held together by its own gravity, burning through nuclear fusion at its core. Every ray of sunlight that touches your skin, every shadow cast by a tree, every golden hour of sunset, all of it comes from this singular star that has been our companion for as long as Earth has existed. Our sun formed approximately 4.6 billion years ago from a vast cloud of gas and dust floating through space. This cloud, called a molecular cloud, began to collapse under its own gravity. As it collapsed, most of the material gathered at the center, growing hotter and denser. Eventually, the pressure and temperature became so extreme that hydrogen atoms began to fuse into helium, releasing tremendous energy. At that moment, the sun ignited. It has been burning steadily ever since, roughly halfway through its expected lifetime of about 10 billion years. When the sun first lit up, Earth had not yet formed. The planets were still gathering themselves from the debris that surrounded the newborn star, slowly accreting into the worlds we know today. When we think of the solar system, we often picture the planets, the moons, the asteroids, and comets. Yet all of these objects combined represent only a tiny fraction of the system's total mass. The sun contains 99.8% of all the matter in the solar system. Jupiter, the largest planet, accounts for most of the remaining mass, while Earth and the other rocky planets are barely noticeable in comparison. This immense mass gives the sun its gravitational dominance, holding all the planets in their orbits and defining the structure of our cosmic neighborhood. Without the sun's enormous gravity, the solar system as we know it would not exist. If you could somehow gather a sample of the sun's material, you would find that it consists almost entirely of two elements, hydrogen and helium. Roughly 91% of the sun's atoms are hydrogen, while about 9% are helium. Together, these two elements make up approximately 98% of the sun's mass. The remaining 2% consists of heavier elements like oxygen, carbon, nitrogen, silicon, magnesium, neon, iron, and sulfur. These heavier elements, though scarce, are crucial for understanding the Sun's history. They were not present when the universe first formed. Instead, they were created inside earlier generations of stars, then scattered into space when those stars died. The Sun formed from this enriched material, making it what astronomers call a population 1 star, relatively rich in heavy elements compared to the oldest stars in the galaxy. Astronomers classify stars based on their temperature, brightness, and size. The Sun falls into a category known as a yellow dwarf, or more technically, a G-type main sequence star. Despite the name, the Sun is not particularly small. It is actually brighter than about 85% of all stars in the Milky Way, most of which are dim red dwarfs. The Sun's surface temperature of about 5,500 degrees Celsius gives it a yellowish-white color when viewed from space. From Earth's surface, atmospheric scattering makes it appear more yellow or orange, especially near the horizon. The term dwarf simply distinguishes it from much larger giant stars. In the grand scheme of stellar types, the Sun is a perfectly average, middle-aged star, neither too hot nor too cool, neither too massive nor too small. To truly grasp the Sun's size, imagine placing Earth at the center of the Sun's sphere. You could fit approximately 109 Earths side by side across the Sun's diameter. But that's just in one dimension. If you wanted to fill the Sun's entire volume with Earths, you would need roughly 1.3 million of them. The Sun measures about 1.4 million kilometers across, nearly 900,000 miles. Its circumference stretches over 4 million kilometers. If you could somehow drive a car around the Sun's equator at highway speeds, the journey would take more than 6 months of continuous driving without stopping. Such vastness is difficult to comprehend, yet the Sun is only a medium-sized star. There are giant stars so large that if placed where the Sun sits now, they would extend beyond the orbit of Mars. Deep within the Sun, at its very center, lies the core. This region, though it represents only about 20% of the Sun's radius, is where all of the Sun's energy is generated. Here, temperatures soared to approximately 15 million degrees Celsius, nearly 27 million degrees Fahrenheit. The pressure is equally staggering, more than 200 billion times Earth's atmospheric pressure. Under such extreme conditions, hydrogen nuclei are forced together, overcoming their natural repulsion to fuse into helium. This nuclear fusion releases enormous amounts of energy, which gradually makes its way outward through the Sun's layers. The energy generated in the core today will take hundreds of thousands of years to reach the surface, slowly diffusing through the dense interior before finally escaping into space as the sunlight we see. Every single second, the Sun fuses approximately 620 million metric tons of hydrogen into 616 million metric tons of helium. The difference, 4 million metric tons, is converted directly into energy, according to Einstein's famous equation, E equals mc squared. This tiny fraction of lost mass, less than 1%, produces an astounding 3.8 times 10 to the 26th joules of energy every second. To put this in perspective, if you could somehow capture just 1 second's worth of the sun's energy output, it would be enough to power all of human civilization at current usage rates for over 500,000 years. The sun has been producing energy at this rate for more than 4 billion years, and it will continue to do so for billions more. The sun sits at an average distance of approximately 150 million kilometers from Earth, a distance we call 1 astronomical unit. Light travels at nearly 300,000 kilometers per second, the fastest speed possible in our universe. Even at this incredible velocity, photons leaving the sun's surface take about 8 minutes and 20 seconds to cross the void and reach Earth. This means that when you look at the sun, you are seeing it not as it is right now, but as it was slightly more than 8 minutes ago. If the sun were to suddenly vanish, we would continue to see it shining in the sky for another 8 minutes before the darkness arrived. Similarly, the warmth we feel on a sunny day left the sun's surface over 8 minutes before it touched our skin. The sun is not a uniform ball of gas, but rather a complex structure consisting of several distinct layers, each with its own characteristics. Starting from the center and moving outward, these layers are the core, where fusion occurs, the radiative zone, where energy moves outward through radiation, the convective zone, where hot plasma rises and cooler plasma sinks, the photosphere, the visible surface we see, the chromosphere, a thin pinkish layer above the photosphere, and finally the corona, the sun's extremely hot outer atmosphere. Each layer plays a crucial role in how the sun generates and releases energy. Understanding these layers has helped scientists unravel many of the sun's mysteries, though questions remain, particularly about why the corona is so much hotter than the layers beneath it. When we look at the sun through proper protective filters, we are seeing its photosphere, the layer from which most of the sun's visible light escapes into space. The photosphere is relatively thin, only about 400 to 500 kilometers deep, which is tiny compared to the sun's overall radius of nearly 700,000 kilometers. The temperature at the photosphere ranges from about 6,500 Kelvin at its base to around 4,500 Kelvin at its top. This is significantly cooler than the interior, yet still hot enough to vaporize any known material instantly. The photosphere is not smooth. When viewed through powerful telescopes, its surface appears mottled with granules, each one representing a convection cell where hot plasma rises to the surface, cools, and sinks back down. These granules are constantly shifting and changing, giving the sun's surface a perpetually restless appearance. One of the sun's greatest mysteries is the temperature of its corona, the outermost layer of its atmosphere. Logic would suggest that as you move away from the sun's hot interior, temperatures should decrease. And indeed, they do, falling from 15 million degrees at the core to about 5,500 degrees at the photosphere. But then, something remarkable happens. In the thin transition region above the photosphere, temperatures suddenly begin to rise again. The chromosphere heats to tens of thousands of degrees, and the corona beyond it reaches temperatures of 1 to 3 million degrees Celsius. How can the corona be hundreds of times hotter than the surface beneath it? Scientists have proposed several mechanisms, including magnetic reconnection and wave heating, but the complete answer remains elusive. This puzzle has captivated solar physicists for decades and continues to drive research into the Sun's complex magnetic behavior. Unlike Earth, which rotates as a solid sphere, the Sun is made entirely of plasma and rotates differentially. This means different parts of the Sun rotate at different speeds. At the equator, the Sun completes one rotation approximately every 25 days. At higher latitudes, near the poles, rotation slows to about 35 days. This differential rotation is possible because the Sun has no solid surface to maintain rigid rotation. The varying rotation rates create shearing forces in the Sun's interior, which play a crucial role in generating its magnetic field. These magnetic effects are responsible for sunspots, solar flares, and many other phenomena we observe. Tracking features like sunspots across the Sun's surface was one of the first ways astronomers confirmed that the Sun rotates at all, a discovery made by Galileo and others in the early 17th century. The Sun's tremendous energy output comes from nuclear fusion, specifically through a process called the proton-proton chain reaction. In the Sun's core, where temperatures reach 15 million degrees Celsius, hydrogen nuclei, which are just individual protons, collide at extreme speeds. Occasionally, two protons overcome their mutual electric repulsion and fuse together. Through a series of steps involving the weak nuclear force, one proton converts into a neutron, releasing a positron and a neutrino. This creates deuterium, a heavy form of hydrogen. The deuterium nucleus then captures another proton to form helium-3. Finally, two helium-3 nuclei collide and fuse to create helium-4, releasing two protons back into the mix. The net result is that 4 hydrogen nuclei are converted into one helium nucleus, with a tiny amount of mass transformed into energy. This process happens billions upon billions of times every second, sustaining the Sun's luminosity. When a photon of energy is created in the Sun's core through fusion, it does not immediately fly off into space. Instead, it begins a long, tortuous journey outward through the Sun's interior. In the radiative zone, photons are constantly absorbed and re-emitted by atoms, bouncing around in a random walk. Because the Sun's interior is so dense, a photon might travel only a millimeter before being absorbed and re-emitted in a new direction. This process of radiative diffusion is incredibly slow. It can take anywhere from 100,000 to 1 million years for energy generated in the core to finally reach the surface. Only then can it escape as sunlight. Meanwhile, neutrinos, ghostly particles created during fusion, pass through the entire Sun almost unimpeded, reaching Earth just 8 minutes after they are created. Sunspots are dark patches that appear on the Sun's photosphere, often in pairs or groups. They are regions where the Sun's magnetic field is particularly strong, thousands of times stronger than Earth's magnetic field. These intense magnetic fields inhibit convection, preventing hot plasma from rising to the surface. As a result, sunspots are cooler than their surroundings, typically about 3,500 to 4,500 Kelvin, compared to the 5,500 Kelvin of the normal photosphere. Though cooler, they are still incredibly hot and would glow brightly if seen in isolation. Sunspots appear dark only by contrast with the even brighter surrounding surface. They can be enormous, some large enough to swallow multiple Earths. Sunspots typically last from a few days to a few months before fading away. Their appearance waxes and wanes over an 11-year cycle, rising to a maximum and then declining to a minimum before beginning the cycle anew. The Sun's activity is not constant, but follows a roughly 11-year cycle. At solar minimum, the Sun's surface is relatively calm with few sunspots and minimal solar activity. As the cycle progresses towards solar maximum, sunspots become more numerous and frequent. Solar flares, coronal mass ejections, and other energetic events increase dramatically. Then, as the cycle wanes, activity declines again toward the next minimum. This cycle is driven by the Sun's magnetic field, which flips polarity approximately every 11 years. The North Magnetic Pole becomes the South Pole and vice versa. After 2 cycles, or about 22 years, the magnetic field returns to its original configuration. The solar cycle affects not only the Sun, but also Earth and the entire solar system. During solar maximum, Earth experiences more frequent geomagnetic storms and auroras, and space weather becomes more hazardous for satellites and astronauts. Solar flares are sudden, intense bursts of radiation from the Sun's surface. They occur when magnetic energy that has built up in the solar atmosphere is suddenly released. The energy of a single large flare can be equivalent to millions of 100 megaton hydrogen bombs exploding simultaneously. Flares emit radiation across the entire electromagnetic spectrum, from radio waves to X-rays to gamma rays. The radiation from a flare reaches Earth in just 8 minutes, potentially disrupting radio communications and damaging satellites. Solar flares are often accompanied by coronal mass ejections, huge clouds of charged particles that erupt from the Sun and travel through space. When these particles reach Earth, they can trigger geomagnetic storms that produce beautiful auroras, but can also interfere with power grids and navigation systems. The largest recorded solar flare occurred in 1859, known as the Carrington event, and caused telegraph systems worldwide to fail. Coronal mass ejections, or CMEs, are enormous eruptions of plasma and magnetic field from the Sun's corona. A single CME can eject billions of tons of material into space at speeds ranging from a few hundred to several thousand kilometers per second. When directed toward Earth, a CME takes 1 to 3 days to arrive, depending on its speed. As the cloud of charged particles approaches, it can compress Earth's magnetosphere, triggering geomagnetic storms. These storms can be spectacular, producing vivid auroras visible at much lower latitudes than usual. However, they can also be dangerous. Strong geomagnetic storms have been known to induce currents in power lines, potentially damaging transformers and causing widespread blackouts. They can also disrupt GPS signals, interfere with radio communications, and pose radiation hazards to astronauts in space. Understanding and predicting CMEs is a major focus of space weather forecasting. The Sun continuously emits a stream of charged particles called the solar wind. This wind consists primarily of electrons and protons, along with small amounts of heavier ions. It originates in the Sun's corona, where temperatures are so high that the plasma overcomes the Sun's gravity and streams outward into space. The solar wind is not uniform. Fast solar wind, traveling at speeds of 700 to 800 kilometers per second, emanates from coronal holes, regions where the Sun's magnetic field lines are open to space. Slow solar wind, moving at about 400 kilometers per second, comes from the Sun's equatorial regions. The solar wind carries with it the Sun's magnetic field, stretching it throughout the solar system. This interplanetary magnetic field interacts with the magnetic fields of planets, moons, and other bodies, shaping their magnetospheres and sometimes stripping away their atmospheres over time. The solar wind does not flow forever. Eventually, far from the Sun, it encounters the interstellar medium, the thin gas that fills the space between stars. The region of space dominated by the solar wind is called the heliosphere. It extends well beyond the orbits of the planets, forming a vast bubble that shields the solar system from most galactic cosmic rays. The boundary where the solar wind slows to subsonic speeds is called the termination shock, located about 80 to 100 astronomical units from the Sun. Beyond this lies the heliosheath, a turbulent region where the solar wind is compressed and deflected. Finally, at the heliopause, roughly 120 astronomical units from the Sun, the solar wind's pressure balances the pressure of the interstellar medium. Both Voyager 1 and Voyager 2 spacecraft have crossed this boundary, becoming the first human-made objects to enter interstellar space. When the solar wind reaches Earth, most of it is deflected by our planet's magnetic field. However, some charged particles manage to enter the magnetosphere, particularly near the magnetic poles where the field lines converge. These particles spiral down along the field lines and collide with atoms and molecules in Earth's upper atmosphere, at altitudes of 100 to 400 kilometers. The collisions excite the atmospheric gases, causing them to emit light. Oxygen produces green and red hues, while nitrogen creates blue and purple tones. The result is the aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere, shimmering curtains of light that dance across the polar skies. Auroras are most common and vivid during periods of high solar activity, when the solar wind is stronger and more frequent CMEs strike Earth's magnetosphere. Indigenous peoples around the world have observed and woven stories around these mysterious lights for thousands of years. The Sun will not shine forever. In about 5 billion years, it will exhaust the hydrogen fuel in its core. When this happens, fusion in the core will cease, and the core will begin to contract under its own gravity. This contraction will heat the core and ignite hydrogen fusion in a shell surrounding it. The energy from this shell burning will cause the Sun's outer layers to expand dramatically. Over the course of 1 billion years, the Sun will swell into a red giant, growing to perhaps 200 times its current diameter. Its surface will cool, giving it a reddish hue, but its total luminosity will increase enormously. The expanding Sun will likely engulf Mercury and Venus. Earth's fate is less certain. It might be consumed as well, or it might be pushed into a wider orbit as the Sun loses mass. In either case, Earth will become uninhabitable long before the Sun reaches its red giant phase, as increasing solar luminosity will boil away the oceans in perhaps 1 billion years. Eventually, after spending about 1 billion years as a red giant, the Sun will shed its outer layers in a series of pulsations. These expelled layers will form a glowing shell of gas called a planetary nebula, illuminated by the hot core left behind. This core, no longer generating energy through fusion, will be incredibly dense, packing roughly half of the Sun's original mass into a sphere about the size of Earth. This is a white dwarf, the final stage in the Sun's life. White dwarfs are no longer truly alive in the stellar sense. They shine not from fusion, but simply from residual heat. Over billions of years, a white dwarf will gradually cool, fading from white to yellow to red, and eventually to black. The Sun's white dwarf remnant will drift through the galaxy for trillions of years, a cold cinder of its former self, orbiting the center of the Milky Way in the dark. Just as Earth orbits the Sun itself orbits the center of the Milky Way galaxy. Our galaxy is a vast spiral disk containing hundreds of billions of stars, and the Sun is located about 25,000 to 28,000 light-years from the galactic center. The Sun travels around the galaxy at a speed of approximately 230 kilometers per second, completing one full orbit roughly every 225 to 250 million years. This period is sometimes called a galactic year or cosmic year. Since the Sun formed 4.6 billion years ago, it has completed about 18 to 20 orbits around the Milky Way. During each orbit, the Sun and its planets pass through different regions of the galaxy, encountering varying densities of gas and dust, and occasionally passing through the galaxy's spiral arms. These changes in environment may have subtle effects on the solar system, though their exact impacts remain a subject of study. Though often described as an average star, the Sun is actually more luminous than about 85% of all stars in the Milky Way. The majority of stars are red dwarfs, small, cool stars that burn their fuel slowly and shine dimly. Some red dwarfs are so faint that they would be invisible to the naked eye, even from the distance of the nearest star system. By contrast, the Sun is a bright yellow-white beacon, easily visible from light years away. Of course, there are also stars far more luminous than the Sun. Blue giant stars can be tens of thousands of times brighter, though they are rare and short-lived. The Sun's luminosity places it comfortably in the middle range of stellar brightness. Neither the dimmest candle nor the most brilliant flame, but a steady light that has sustained life on Earth for billions of years. When we think of sunlight, we often picture the bright, visible light that illuminates our world. But visible light represents only a small fraction of the Sun's total energy output. The Sun emits radiation across the entire electromagnetic spectrum. It produces radio waves, which have the longest wavelengths. It emits infrared radiation, which we feel as heat. Beyond visible light, the sun radiates ultraviolet light, which can tan skin and damage DNA. It also emits X-rays and gamma rays, high-energy radiation that would be lethal if it reached Earth's surface in significant quantities. Fortunately, Earth's atmosphere, particularly its ozone layer, absorbs most of the sun's harmful ultraviolet and high-energy radiation. Instruments on satellites above the atmosphere can detect the sun's full spectrum, allowing scientists to study processes occurring at different temperatures and in different layers of the solar atmosphere. The sun is not a static object, but is constantly losing mass. Every second, 4 million metric tons of matter are converted into energy in the core through fusion and radiated away into space. Additionally, the solar wind carries away about 1 to 3 billion kilograms of material every second. Over the sun's lifetime of billions of years, these losses add up. Since it formed, the sun has lost roughly 1 part in 10,000 of its original mass. While this might seem insignificant, the lost mass has subtle effects on the orbits of the planets. As the sun becomes less massive, its gravitational pull weakens slightly, and the planet's orbits gradually expand outward. By the time the sun becomes a red giant, and then a white dwarf, it will have lost about half of its total mass, dramatically altering the architecture of the solar system that remains. The sun's enormous mass creates a powerful gravitational field that extends throughout the solar system. This gravity is what keeps all the planets, dwarf planets, asteroids, and comets in their orbits around the sun. Without the sun's gravity, these objects would fly off into interstellar space. The balance between a planet's orbital speed and the sun's gravitational pull determines the shape and size of its orbit. Earth, for example, travels around the sun at about 30 kilometers per second, fast enough that it continually falls toward the sun, but also moves sideways fast enough to keep missing it, tracing an elliptical path through space. The sun's gravity dominates the inner solar system completely, even at the distance of Neptune. 30 astronomical units away, the sun's gravity is still strong enough to hold the planet in a stable orbit, keeping it bound to our star for billions of years. While sunlight reaches Earth in just over 8 minutes, it takes significantly longer to reach the outer solar system. Pluto, which orbits at an average distance of about 40 astronomical units from the Sun, receives sunlight that has been traveling for approximately 5.5 hours. At that distance, the Sun appears much smaller and dimmer than it does from Earth, though it is still far brighter than any other star in the sky. The intensity of sunlight diminishes with the square of the distance, meaning that Pluto receives only about 1/1600th of the sunlight that Earth does. Despite this, the Sun still provides enough light and heat to make Pluto's nitrogen ice sublimate during its closest approach, creating a thin atmosphere that freezes again as Pluto moves farther away. Even at such vast distances, the Sun's influence is felt. The Sun's gravitational influence doesn't end with the planets. Far beyond Neptune lies the Oort cloud, a vast spherical shell of icy bodies that surrounds the solar system. This cloud is thought to extend from about 2,000 astronomical units out to perhaps 100,000 astronomical units from the Sun, nearly halfway to the nearest star. Objects in the Oort cloud are so distant that they take millions of years to complete a single orbit, and the Sun appears merely as the brightest star in their sky. Yet even at these enormous distances, the Sun's gravity is sufficient to keep these icy bodies loosely bound to the solar system. Occasionally, gravitational perturbations from passing stars or giant molecular clouds nudge Oort cloud objects inward, sending them plunging toward the Sun as long-period comets. These frozen wanderers are remnants from the solar system's formation, preserving in their icy cores clues to the conditions that existed 4.6 billion years ago. Deep in the Sun's core, the nuclear fusion reactions that power the star produce not only energy, but also ghostly particles called neutrinos. Neutrinos are nearly massless and interact so weakly with matter that they can pass through entire planets as if they weren't there. Every second, the Sun produces an unimaginable number of neutrinos, and trillions of them pass through your body each second without you noticing. Because neutrinos barely interact with anything, they escape the Sun's core immediately, reaching Earth in just 8 minutes, unlike the light, which takes hundreds of thousands of years to diffuse out through the Sun's interior. Detecting solar neutrinos is extremely difficult, requiring massive underground detectors filled with special materials. When scientists finally succeeded in detecting solar neutrinos in the 1960s, they found fewer than expected, a puzzle that became known as the solar neutrino problem. It was eventually resolved with the discovery that neutrinos can change type as they travel, a phenomenon called neutrino oscillation. If you could look at the Sun's surface through a powerful telescope equipped with proper filters, you would see that it is not smooth, but covered with a constantly shifting pattern of bright cells called granules. Each granule is the top of a convection cell, a vast column of hot plasma rising from deeper within the Sun. The bright center of a granule is where hot material reaches the surface, and the darker boundaries are where cooler material sinks back down. Each granule is enormous, typically about 1,000 kilometers across, roughly the size of France or Texas. They appear, evolve, and disappear in a matter of minutes as the convection continuously churns the Sun's outer layers. Watching this granulation is like watching water boil, a visible manifestation of the tremendous heat flowing from the Sun's interior to its surface. Larger convection patterns, called supergranules, span tens of thousands of kilometers and last about a day. The average distance from Earth to the Sun is about 150 million kilometers, or 93 million miles. This distance is called an astronomical unit, and it serves as a convenient measuring stick for distances within the solar system. Earth's orbit is not a perfect circle, but an ellipse, so the actual distance varies throughout the year. At perihelion, when Earth is closest to the Sun, the distance is about 147 million kilometers. At aphelion, when Earth is farthest, it's about 152 million kilometers. Interestingly, Earth is closest to the Sun in early January, during winter in the Northern Hemisphere, demonstrating that the seasons are caused by the tilt of Earth's axis, not by changes in distance. The distance to the Sun is one of the most important measurements in astronomy, as it forms the baseline for determining the distances to other stars and galaxies through geometric parallax. Long before modern science explained the Sun's nature, ancient cultures around the world recognized its vital importance and often elevated it to the status of a deity. In ancient Egypt, Ra was the sun god, believed to journey across the sky in a solar boat each day and through the underworld each night. The Aztecs worshipped Tonatiuh, the sun god, and believed that human sacrifice was necessary to ensure the sun would continue to rise. In Greek mythology, Helios drove the chariot of the sun across the sky daily. The Inca Empire revered Inti, the sun god, as the ancestor of their emperors. Many ancient monuments were aligned with solar events, such as solstices and equinoxes, demonstrating the deep connection between human societies and the sun's movements. Stone circles, pyramids, and temples around the world mark the passage of the sun through the seasons, embodying humanity's ancient understanding that our very existence depends upon the light and warmth of this celestial body. While the sun won't become a red giant for another 5 billion years, Earth's time as a habitable world is much shorter. The sun's luminosity is gradually increasing, about 10% every billion years, as helium accumulates in the core and slightly alters the fusion process. In approximately 600 million to 1 billion years, this increased luminosity will heat Earth to the point where the carbon cycle, which currently regulates Earth's climate, will break down. Plants will no longer be able to photosynthesize efficiently, and most complex life will die out. In another few 100 million years, the oceans will begin to evaporate, and Earth will enter a runaway greenhouse state similar to Venus. By the time the sun reaches its red giant phase, Earth will already have been a lifeless, scorched rock for billions of years. If humanity or its descendants wish to survive beyond this time frame, they will need to find new homes around other, younger stars. One of the reasons life has flourished on Earth is the sun's remarkable stability. Over timescales of millions to billions of years, the sun's energy output has remained relatively constant, varying by only a few percent. This stability is the result of a delicate balance between the inward pull of gravity and the outward pressure from fusion reactions in the core. If fusion increases slightly, the core heats up and expands, which reduces density and slows the fusion rate. If fusion decreases, the core contracts, heats up, and fusion accelerates again. This self-regulating mechanism, called hydrostatic equilibrium, keeps the sun shining steadily. Even during the 11-year solar cycle, the sun's total energy output varies by less than 0.1%. This stability is not shared by all stars. Some stars pulsate dramatically, varying their brightness by factors of hundreds or thousands. Others undergo sudden flares or outbursts. Earth's fortune is to orbit a calm, stable star. From Earth's surface, the sun appears yellow or yellowish-white, especially when high in the sky. However, the sun's actual color is closer to white. The yellowish tint we observe is due to Earth's atmosphere, which scatters shorter wavelengths of light like blue and violet, more than longer wavelengths like red and yellow. This scattering is why the sky appears blue and why the sun looks more yellow. Near sunrise and sunset, when sunlight passes through more atmosphere, even more blue light is scattered away, leaving only the longer wavelengths to reach our eyes. This is why the sun and sky take on orange and red hues during twilight. Astronauts viewing the sun from space, without the filtering effect of an atmosphere, would see it as brilliant white. The sun emits light at all visible wavelengths, and when combined, they produce white light. Only atmospheric effects give it the warm yellow glow we associate with a sunny day. While hydrogen and helium dominate the sun's composition, spectroscopic analysis has revealed the presence of more than 60 different chemical elements. These include oxygen, carbon, nitrogen, silicon, magnesium, neon, iron, and sulfur, among many others. Most of these heavier elements exist in trace amounts, making up roughly 2% of the sun's total mass. The presence of these elements tells us about the sun's heritage. When the universe began, only hydrogen, helium, and traces of lithium existed. All heavier elements were forged in the cores of earlier generations of stars through nuclear fusion. When those stars died, some as supernovae, they scattered these elements into space. The cloud from which the sun formed contained material from countless previous stellar generations. We can detect these elements by analyzing the sun's spectrum, the rainbow of colors created when sunlight is split by a prism or diffraction grating. Each element absorbs or emits light at specific wavelengths, leaving dark lines or bright lines in the spectrum that serve as chemical fingerprints. Humans have observed the sun since prehistoric times. Ancient astronomers tracked its movement across the sky, noting the changing length of days through the seasons. The Chinese kept detailed records of sunspots as early as 28 BCE. In the 17th century, Galileo Galilei used one of the first telescopes to observe sunspots, providing evidence that the sun rotated and was not the perfect, unchanging sphere that some had believed. His observations challenged prevailing views and contributed to the scientific revolution. In the 19th century, scientists began to use spectroscopy to study the sun's composition. In 1868, during a total solar eclipse, observers detected a mysterious yellow spectral line that did not match any known element. They attributed it to a new element and named it helium, after Helios, the Greek sun god. It was not found on Earth until years later. Today, space-based observatories like the Solar Dynamics Observatory continuously monitor the sun, capturing images and data that help us understand its complex behavior in unprecedented detail. The sun possesses a powerful and intricate magnetic field that permeates its atmosphere and extends throughout the solar system. Unlike Earth's relatively simple dipolar magnetic field resembling a bar magnet, the sun's magnetic field is tangled and constantly changing. It is generated by the movement of electrically charged plasma in the sun's interior, particularly in the convective zone. The Sun's differential rotation, spinning faster at the equator than at the poles, stretches and twists the magnetic field lines. Over time, these field lines become increasingly tangled, eventually bursting through the surface to create sunspots, solar flares, and coronal mass ejections. Every 11 years, the Sun's magnetic field flips, with the north and south magnetic poles switching places. This magnetic activity drives much of the Sun's dynamic behavior and is responsible for the phenomena collectively known as space weather, which can affect Earth and other planets. Based on the amount of hydrogen remaining in its core and the rate at which it is being consumed, the Sun has enough fuel to continue shining in its current state for approximately another 5 billion years. This may seem like an incomprehensibly long time, and indeed it is. 5 billion years ago, Earth itself was still forming. Complex life on Earth has existed for perhaps 600 million years, and humans for only a few 100,000. The Sun's remaining lifespan is so vast that it dwarfs all of recorded human history many thousands of times over. Yet eventually, the hydrogen fuel will run out. The core will contract, temperatures will rise, and the Sun will begin burning helium, transitioning to the red giant phase. Even then, it will continue to shine for billions more years, albeit in a very different form. Stars like the Sun are among the longest-lived structures in the universe. Prominences are enormous loops and arcs of plasma that extend from the Sun's surface into the corona. They follow the Sun's magnetic field lines, which can stretch tens or even hundreds of thousands of kilometers above the photosphere. Prominences are cooler and denser than the surrounding corona, which is why they appear bright when seen at the Sun's edge during an eclipse, or with certain instruments. Some prominences are quiescent, lasting for weeks or even months, while others are eruptive, hurling material into space. When seen against the bright solar disk, prominences appear dark and are called filaments. These structures can be extraordinarily large, sometimes exceeding the diameter of Earth by several times. A single prominence might contain billions of tons of plasma suspended in the Sun's magnetic field. When they erupt, they can trigger coronal mass ejections, sending vast clouds of charged particles speeding toward Earth and other planets. The Sun is not silent. Though sound cannot travel through the vacuum of space, the Sun's interior is filled with sound waves that resonate throughout its body. These waves are created by turbulent convection in the outer layers and cause the Sun's surface to oscillate, rising and falling by small amounts. By observing these oscillations, scientists can study the Sun's internal structure in a field called helioseismology, similar to how geologists use seismic waves to study Earth's interior. Different sound waves penetrate to different depths, and by analyzing their frequencies and behavior, researchers can determine the temperature, composition, and motion of material throughout the Sun. These oscillations are subtle, typically only a few meters per second, but they provide invaluable insights. Helioseismology has confirmed models of the Sun's interior, revealed the differential rotation inside the Sun, and helped identify the location of the convective zone. In a sense, the Sun rings like a bell, and we can listen to learn its secrets. Under normal circumstances, the sun's photosphere is so bright that it completely overwhelms the faint glow of the corona. But during a total solar eclipse, when the moon passes directly between Earth and the sun, the moon's disk blocks the photosphere, allowing the corona to become visible. For a few precious minutes, observers in the path of totality can see the corona's delicate, pearly white streamers stretching outward from the darkened sun. Before the advent of space-based observatories, total solar eclipses were the only time scientists could study the corona in detail. Astronomers would travel to remote locations to observe eclipses, hoping for clear skies and good weather. These expeditions led to many discoveries, including the identification of helium and the measurement of the sun's corona temperature. Today, instruments called coronagraphs can artificially block the sun's bright disk, allowing continuous observation of the corona. Nevertheless, total solar eclipses remain awe-inspiring events, offering the public a chance to witness one of nature's most spectacular sights. The story of the sun begins with a giant molecular cloud, a vast region of gas and dust drifting through the Milky Way galaxy. About 4.6 billion years ago, something disturbed this cloud, perhaps the shock wave from a nearby supernova explosion. The disturbance caused a portion of the cloud to begin collapsing under its own gravity. As it collapsed, the material heated up and spun faster, flattening into a rotating disk. Most of the mass accumulated at the center, forming a dense, hot protostar. Over time, as more material fell inward, the protostar grew hotter and denser. When the core temperature reached about 10 million degrees Celsius, hydrogen fusion ignited and the sun was born. The remaining material in the disk eventually coalesced into planets, moons, asteroids, and comets. This process of star formation is happening throughout the galaxy even today. Molecular clouds like the one that birthed the sun are stellar nurseries, giving rise to new generations of stars. Stars are classified into populations based on their composition. Population 3. Stars are the hypothetical first stars, formed from the primordial hydrogen and helium created in the Big Bang. They contained no heavy elements. Population 2 stars formed later, after the first generation of stars had enriched the interstellar medium with small amounts of heavier elements. Population 1 stars, like the Sun, are relatively rich in heavy elements, formed from material that had been processed through its multiple generations of stellar evolution. The presence of elements like carbon, oxygen, and iron in the Sun's composition indicates that the cloud from which it formed had been enriched by many previous stars. These heavy elements are crucial for planet formation and for the chemistry of life. Rocky planets like Earth could not exist without the silicon, iron, and other elements forged in ancient stars. We are, quite literally, made of stardust. While the Sun's total energy output varies only slightly over the solar cycle, certain wavelengths change more dramatically. Ultraviolet radiation, particularly in the extreme UV range, increases by several times during solar maximum compared to solar minimum. This has direct effects on Earth's upper atmosphere. Increased UV radiation heats the thermosphere, causing it to expand. This expansion increases atmospheric drag on satellites in low Earth orbit, altering their orbits and potentially shortening their operational lifetimes. The ionosphere, a layer of charged particles in the upper atmosphere, also responds to changes in solar UV, affecting radio wave propagation and GPS signals. By monitoring the sun's UV output, scientists can better predict these effects and mitigate their impacts on technology. Instruments aboard satellites continuously measure the sun's spectrum across all wavelengths, providing data that feeds into space weather forecasting models. The sun is the primary driver of Earth's climate, providing the energy that warms the planet and drives weather patterns. Over short timescales, the sun's influence on climate is relatively constant, though the 11-year solar cycle does produce small variations. Some studies suggest a weak correlation between solar activity and certain climate patterns, though these effects are minor compared to other factors like greenhouse gas concentrations. Over longer timescales, changes in Earth's orbit and axial tilt, known as Milankovitch cycles, alter the distribution and intensity of sunlight reaching different parts of Earth, contributing to ice ages and interglacial periods. These cycles operate over tens to hundreds of thousands of years. Additionally, the sun's brightness has increased by about 30% since it formed 4.6 billion years ago, a phenomenon known as the faint young sun paradox. Early Earth should have been frozen solid, yet evidence shows liquid water existed. This suggests that greenhouse gases or other factors kept early Earth warm despite the weaker sun. In addition to light and the steady solar wind, the sun occasionally releases high-energy particles during solar flares and coronal mass ejections. These particles, primarily protons and electrons accelerated to near-light speeds, can reach Earth within minutes to hours. When they arrive, they can penetrate satellites, damage electronics, and pose radiation hazards to astronauts in space or even airline passengers flying at high altitudes during polar routes. Earth's magnetic field provides some protection, funneling most of these particles toward the poles, where they can create beautiful auroras. However, during particularly strong events, these particles can reach lower latitudes, increasing the risk. The study of solar energetic particles is an important part of space weather research. Forecasters monitor the sun for flares and other activity that might produce dangerous particle events, providing warnings to satellite operators, airlines, and space missions so they can take protective measures. We cannot see inside the sun directly. The photosphere is opaque, and all layers beneath it are hidden from view. However, scientists have developed ways to probe the sun's interior. Helioseismology, which studies the sun's oscillations, allows researchers to infer the properties of the layers below the surface. Computer models of stellar structure, based on the laws of physics and observations of the sun's surface, provide detailed predictions of conditions inside the sun. These models agree remarkably well with helioseismic observations, giving us confidence in our understanding. Neutrino detectors provide another window into the core. Since neutrinos escape the sun immediately, they carry information about fusion reactions happening in real time. By detecting and analyzing these neutrinos, scientists can test their models of the sun's core. Through these indirect methods, We have mapped the Sun's interior with impressive accuracy, even though we will never be able to see it directly. Given the Sun's enormous size, it might seem that its visible surface would be thick and substantial. In fact, the photosphere is remarkably thin, only about 400 to 500 kilometers deep. Below that depth, the Sun's plasma is opaque, absorbing all light. Above it, the plasma becomes increasingly transparent, allowing photons to escape. This narrow zone is what we see when we look at the Sun. The photosphere's thinness is one reason the Sun appears to have such a sharp edge. In reality, there is no solid surface, just a gradual transition from opaque to transparent plasma. The temperature in the photosphere ranges from about 6,500 Kelvin at the bottom to 4,500 Kelvin at the top. This temperature gradient is why the photosphere is not uniform in brightness. Cooler regions, like sunspots, appear darker, while hotter regions shine more brightly. When the Sun formed 4.6 billion years ago, it likely rotated much faster than it does today. Young stars similar to the Sun have been observed to complete a rotation in just a few days. Over time, the Sun's rotation has slowed due to a process called magnetic braking. The Sun's magnetic field interacts with the solar wind, extending far into space. As the solar wind carries away charged particles, it also carries angular momentum, gradually slowing the Sun's rotation. This process continues today, though the effect is very gradual. Observing the rotation rates of stars of different ages allows astronomers to study stellar evolution and understand how stars like the Sun change over their lifetimes. The Sun's rotation is intimately tied to its magnetic activity. Slower rotation may eventually lead to reduced magnetic field generation, which could affect sunspot activity and space weather in the distant future. When the Sun's energy arrives at Earth, it does so in several forms. The most obvious is electromagnetic radiation, spanning from radio waves to gamma rays, though the bulk of the energy is in the visible and infrared parts of the spectrum. This radiation warms the planet, drives photosynthesis, and powers weather systems. The solar wind, a stream of charged particles, also carries energy, though it is mostly deflected by Earth's magnetic field. During geomagnetic storms, some of this energy enters the magnetosphere and ionosphere, heating the upper atmosphere and creating auroras. Additionally, solar energetic particles accelerated during flares and CMEs bring energy in the form of high-speed protons and electrons. Even neutrinos from the Sun's core, though they interact weakly, carry a tiny fraction of the Sun's energy through Earth. All these forms of energy combine to sustain the delicate balance that makes life possible on our planet. Every second, the Sun loses mass through two primary processes: the conversion of mass to energy via fusion, and the expulsion of matter via the solar wind. The fusion process converts about 4 million metric tons per second into energy. Meanwhile, the solar wind carries away roughly 1 to 3 billion kilograms of material every second. While these numbers sound enormous, they are tiny compared to the Sun's total mass of nearly 2 times 10 to the 30th kilograms. Over the Sun's 4.6 billion year history, it has lost roughly 1 part in 10,000 of its mass. As the Sun continues to age, especially during the red giant phase, it will lose mass much more rapidly. By the time it becomes a white dwarf, it will have shed nearly half of its original mass. This mass loss will weaken the Sun's gravity, causing the orbits of the remaining planets to expand, slowly drifting outward into the cold dark of space. Helioseismic studies have revealed that the Sun's internal rotation is complex. While the photosphere rotates differentially, with the equator faster than the poles, the interior rotation pattern is different. Deep below the convective zone, in the radiative zone, the Sun rotates almost like a solid body with minimal differential rotation. The transition between these two regimes occurs at the boundary between the radiative and convective zones, a region called the tachycline. This shear layer, where rotation rates change sharply, is thought to play a crucial role in generating the Sun's magnetic field. The differing rotation rates create shearing forces that twist and amplify magnetic field lines, eventually causing them to break through the surface as sunspots and other magnetic phenomena. Understanding the tachycline and its role in the solar dynamo remains an active area of research in solar physics. Light from the Sun carries not only energy, but also momentum. When photons strike an object, they exert a tiny force called radiation pressure. For everyday objects on Earth, this force is negligible, overwhelmed by gravity and air resistance. But in the vacuum of space, where other forces are weak or absent, radiation pressure can have significant effects. It pushes on spacecraft, altering their orbits slightly over time. It shapes the dust tails of comets, causing them to always point away from the Sun, regardless of the comet's direction of travel. Scientists and engineers have proposed using radiation pressure for propulsion, deploying large reflective solar sails that could accelerate spacecraft without the need for fuel. Although the force is small, given enough time, a spacecraft propelled by sunlight alone could reach high speeds. Several missions have successfully tested solar sail technology, demonstrating that we can navigate the solar system using the light of the Sun itself. At approximately 4.6 billion years old, the Sun is roughly halfway through its main sequence lifetime. It has been fusing hydrogen in its core for billions of years, and will continue to do so for billions more. In stellar terms, this makes the Sun middle-aged. It is neither a young, newly formed star, which might be more variable and active, nor an old, dying star approaching the end of its life. The Sun's middle age is a stable period, characterized by steady energy output and relatively calm behavior compared to younger stars. This stability has been crucial for the development of life on Earth. Had the Sun been more variable, with dramatic changes in brightness or frequent superflares, life might never have gained a foothold on our planet. We orbit a mature, reliable star, and that has made all the difference. When the Sun first ignited 4.6 billion years ago, it was about 30% less luminous than it is today. This presents a puzzle known as the faint young sun paradox. According to models, early Earth should have been frozen solid under such weak sunlight. Yet geological evidence clearly shows that liquid water existed on Earth's surface, more than 3.8 billion years ago. Several explanations have been proposed to resolve this paradox. Early Earth's atmosphere may have contained much higher concentrations of greenhouse gases like carbon dioxide and methane, trapping enough heat to keep the planet warm. Alternatively, Earth's surface might have been darker, absorbing more of the available sunlight. As the sun has aged, it has grown brighter, and Earth's climate has adjusted in tandem, regulated by the carbon cycle and other feedback mechanisms. This interplay between a slowly brightening sun and Earth's evolving atmosphere has shaped the history of life on our planet. After the sun becomes a white dwarf, it will no longer generate energy through fusion. Instead, it will shine simply from the residual heat left over from its previous life. White dwarfs cool extremely slowly, radiating their stored thermal energy over unimaginably long timescales. For the first few billion years, the sun's white dwarf remnant will glow white hot, gradually fading through yellow, orange, and red as it cools. Eventually, after tens of billions of years, it will dim to the point of invisibility, becoming a black dwarf, a cold, dark cinder. However, the universe is currently only about 14 billion years old, not old enough for any white dwarf to have cooled completely. The sun's white dwarf will drift through the galaxy for trillions of years, a silent monument to the star that once gave life to Earth. Long ago, after the last remnants of human civilization have vanished, the sun will continue its lonely journey through the cosmos. The sun's magnetic field does not end at its surface. Carried outward by the solar wind, the interplanetary magnetic field extends throughout the heliosphere, reaching far beyond the orbit of Pluto. This field has a complex structure, shaped by the sun's rotation and the properties of the solar wind. One prominent feature is the heliospheric current sheet, a vast wavy surface where the magnetic field changes polarity. This sheet stretches throughout the solar system, rotating with the sun like a giant undulating skirt. Spacecraft traveling through the solar system cross this sheet multiple times, experiencing reversals in the direction of the magnetic field. The interplanetary magnetic field influences how cosmic rays, high-energy particles from outside the solar system, penetrate into the inner solar system. When the sun's magnetic field is strong, it provides better shielding, reducing the flux of cosmic rays reaching Earth. Astronauts and satellites are vulnerable to the sun's activity. During solar flares and coronal mass ejections, the flux of high-energy particles increases dramatically. These particles can damage sensitive electronics, disrupt communications, and pose serious radiation hazards to humans in space. On Earth's surface, we are protected by the atmosphere and magnetic field, but astronauts aboard the International Space Station or on future missions to the Moon and Mars have much less protection. Space agencies closely monitor the sun's activity, and missions are planned to minimize exposure during periods of high solar activity. Satellites in orbit can also be damaged or destroyed by geomagnetic storms. Electrical currents induced by changing magnetic fields can overload circuits, and increased atmospheric drag during storms can alter orbits. Understanding and predicting space weather is essential for the safety and success of space exploration. By analyzing the sun's spectrum, scientists can determine which elements are present and in what proportions. These measurements reveal that the sun's composition closely matches the primordial composition of the gas cloud from which it formed, though enriched with heavier elements from previous generations of stars. Comparing the sun's composition to that of meteorites, which are among the oldest solid objects in the solar system, provides insights into the conditions present during the solar system's formation. Small differences between the sun's composition and that of Earth, known as the solar abundance pattern, help scientists understand how planets formed and how material was processed in the protoplanetary disk. The sun's composition is a snapshot of the chemical makeup of our corner of the galaxy 4.6 billion years ago, a record written in light. Below the convective zone lies the radiative zone, extending from about 25% of the sun's radius out to about 70%. In this region, energy moves outward not by convection, but through the slower process of radiative diffusion. Photons are constantly absorbed and re-emitted by the densely packed plasma, taking an incredibly long time to travel through. The radiative zone is extremely dense, with densities ranging from about 150 grams per cubic centimeter near the core to about 0.2 grams per cubic centimeter at the top. For comparison, Earth's atmosphere at sea level has a density of only about 0.001 grams per cubic centimeter. Despite this high density, the radiative zone is entirely plasma, with electrons stripped from nuclei due to the extreme temperatures. The intense pressure and temperature make the radiative zone one of the most extreme environments in the solar system. All life on Earth depends, directly or indirectly, on the sun. Plants, algae, and certain bacteria capture sunlight through photosynthesis, converting carbon dioxide and water into glucose and oxygen using the sun's energy. This process forms the base of nearly all food chains. Herbivores eat plants, carnivores eat herbivores, and so on. Even organisms that live in the deep ocean, far from sunlight, often rely on organic matter that originated from photosynthetic organisms at the surface. The oxygen in Earth's atmosphere, which most life requires for respiration, is also a byproduct of photosynthesis. Without the sun's steady light, photosynthesis would cease, and the intricate web of life on Earth would quickly collapse. Fossil fuels, like coal, oil, and natural gas, are ancient stores of solar energy, captured by photosynthetic organisms millions of years ago and transformed over time. In a very real sense, the sun has been fueling life on Earth for billions of years. During a total solar eclipse, when the moon completely blocks the sun's bright photosphere, the corona becomes visible as a faint pearly white halo surrounding the darkened disk. The corona's appearance changes depending on the phase of the solar cycle. At solar minimum, the corona often displays long, graceful streamers near the equator and more confined structures near the poles. At solar maximum, the corona appears more irregular and complex, with loops and prominences extending in all directions. Observers have traveled the world for centuries to witness this breathtaking sight, and total eclipses remain among nature's most awe-inspiring spectacles. Today, while satellites can observe the corona continuously using coronagraphs, nothing quite matches the experience of standing in the moon's shadow and watching the corona shimmer above the horizon. It is a visceral reminder of the dynamic, powerful star that sustains us. Above the radiative zone lies the convective zone, extending from about 70% of the Sun's radius all the way to the photosphere. In this region, plasma is cool enough that it becomes opaque, trapping heat and causing convection. Hot plasma rises toward the surface, cools as it releases energy, and then sinks back down. This roiling motion creates the granulation pattern visible on the photosphere. The convective zone is also where the Sun's magnetic field is thought to be generated through dynamo action. The movement of electrically conducting plasma, combined with the Sun's rotation, twists and amplifies magnetic field lines. Turbulent convection also excites sound waves that propagate through the Sun's interior, creating the oscillations studied by helioseismology. The convective zone is a dynamic, chaotic region, and understanding its behavior is key to unraveling many of the Sun's mysteries. The photosphere, the Sun's visible surface, has a temperature of approximately 5,500 degrees Celsius, or 10,000 degrees Fahrenheit. This is hot enough to vaporize any known substance instantly. Yet compared to the core's 15 million degrees, or the corona's million-degree temperatures, the photosphere is relatively cool. The temperature of the photosphere is what gives the Sun its yellow-white color. Hotter stars appear blue or white, while cooler stars appear orange or red. The Sun's temperature places it squarely in the middle of the stellar spectrum. At this temperature, atoms in the photosphere are partially ionized, with some electrons stripped away but many still bound to their nuclei. This partially ionized state affects how the Sun absorbs and emits light, producing the intricate patterns of absorption lines seen in the solar spectrum. From Earth, the Sun and Moon appear almost the same size in the sky, which is why the Moon can completely cover the Sun during a total solar eclipse. However, this is purely coincidental. The Sun is about 400 times larger in diameter than the Moon, but it is also about 400 times farther away. These two effects cancel out, making them appear nearly equal in angular size. This cosmic coincidence means that during total solar eclipses, the Moon's disk fits almost perfectly over the Sun, revealing the corona without blocking too much of it. If the Moon were slightly smaller or farther from Earth, we would only see annular eclipses, where a ring of the Sun's surface remains visible. If the Moon were larger or closer, it would block the corona entirely. Earth is one of the few places in the solar system where such perfectly matched eclipses occur. Unlike many aspects of nature, the Sun's future is well understood. Stellar evolution theory, supported by observations of countless other stars at different life stages, allows astronomers to predict with confidence what will happen to the Sun over the next billions of years. It will continue to fuse hydrogen in its core for about another 5 billion years, gradually growing brighter. Then it will expand into a red giant, fusing helium and eventually shedding its outer layers. Finally, it will settle into a white dwarf, cooling slowly over trillions of years. These predictions are based on well-tested physics and the laws of thermodynamics, gravity, and nuclear reactions. While the details may vary slightly, the overall trajectory is certain. The sun's life cycle is as inevitable as the changing of seasons, written into the fabric of the universe itself. Comets originating from the distant Oort cloud or the Kuiper belt follow highly elliptical orbits around the sun. As they approach the inner solar system, the sun's gravity accelerates them to tremendous speeds. As they swing around the sun and head back outward, they slow down again, spending most of their time in the cold outer reaches. The sun's gravity determines these orbital paths precisely. Some comets make periodic returns, like Halley's Comet, which orbits every 76 years. Others make only a single pass before being flung out of the solar system entirely or plunging into the sun. The sun's gravity also causes tidal forces that can break apart loosely bound comets, splitting them into multiple fragments. Studying cometary orbits helps scientists understand the gravitational dynamics of the solar system and the distribution of objects in its distant reaches. The sun's gravity is the invisible sculptor of these icy wanderers' paths through space. The warmth we feel on a sunny day is the result of infrared radiation from the sun being absorbed by our skin. This radiation, though invisible to our eyes, carries substantial energy. When it strikes matter, it causes molecules to vibrate faster, increasing temperature. This heating effect is fundamental to Earth's climate. Sunlight warms the surface, which heats the atmosphere above it. Differences in heating between the equator and poles drive atmospheric circulation, creating winds and weather patterns. Oceans absorb sunlight, storing vast amounts of heat that redistributes around the globe through currents. Without the sun's warmth, Earth would be a frozen, lifeless world with temperatures hovering around negative 270 degrees Celsius, barely above absolute zero. The gentle warmth of a sunbeam is a manifestation of the nuclear fusion occurring in the sun's core, energy that has traveled 150 million kilometers to reach us. Unlike the solid, liquid, and gas we encounter in everyday life, the sun is made of plasma, sometimes called the fourth state of matter. Plasma is a gas that has been heated to such high temperatures that electrons are stripped from atoms, creating a mixture of free electrons and positively charged ions. Plasma behaves differently from ordinary gas. It conducts electricity, responds to magnetic fields, and can carry electric currents. The sun's entire structure, from core to corona, is plasma. This gives the sun properties that would be impossible for a solid or liquid body. Magnetic field lines can twist and tangle within the plasma, storing enormous amounts of energy that can be suddenly released in flares and eruptions. Plasma flows and convects, creating the dynamic, ever-changing surface we observe. Understanding plasma physics is essential to understanding the sun and stars. After the sun becomes a black dwarf, cooling until it no longer emits visible light, it will effectively become invisible. It will still exist as a dense, dark remnant drifting through space, but without fusion or significant heat, it will produce no light. Any planets or asteroids that remain in orbit around it will circle in eternal darkness. The black dwarf sun will be detectable only through its gravitational influence, or by the faint glow of residual infrared radiation that might linger for trillions upon trillions of years. However, this ultimate fate is so far in the future that it is nearly incomprehensible. The universe itself may undergo fundamental changes long before the sun reaches this final dark state. For now, the sun shines brightly, a beacon of light and life in the cosmos, and it will continue to do so for billions of years to come. While the sun currently fuses hydrogen into helium when it becomes a red giant, it will begin fusing helium into heavier elements like carbon and oxygen. This process, called helium burning or the triple alpha process, occurs at higher temperatures and pressures than hydrogen fusion. 3 helium-4 nuclei combine to form a carbon-12 nucleus, releasing energy. Further fusion can produce oxygen-16. However, the sun is not massive enough to fuse elements heavier than carbon and oxygen. More massive stars can continue the fusion process, creating elements up to iron. Elements heavier than iron are formed only in supernova explosions or neutron star collisions. The carbon and oxygen created in the sun's core during its red giant phase will eventually become part of the planetary nebula it ejects, enriching the interstellar medium. Future generations of stars and planets will incorporate these elements, continuing the cosmic cycle of creation. According to Einstein's theory of general relativity, massive objects like the sun bend the fabric of space-time. This curvature is what we perceive as gravity. The sun's immense mass creates a deep well in space-time, and objects like planets move along the curved paths defined by this well. Light passing near the sun is also bent by this curvature, an effect called gravitational lensing. During a total solar eclipse in 1919, astronomers measured the positions of stars near the sun and found that their apparent positions were shifted, exactly as Einstein's theory predicted. This experiment provided one of the first major confirmations of general relativity. The sun's influence on space-time extends throughout the solar system, affecting the motion of everything from Mercury to distant comets. In a very real sense, the sun shapes the geometry of space itself. Astronomers use the term luminosity to describe the total amount of energy a star emits per second. The sun's luminosity is approximately 3.8 times 10 to the 26th watts, an almost incomprehensible number. This is equivalent to about 300 trillion light bulbs shining simultaneously. Luminosity depends on a star's size and temperature. Larger, hotter stars are more luminous, while smaller, cooler stars are less luminous. The sun's luminosity places it in the middle range compared to other stars. Red dwarfs can have luminosities of only 1/1000th of the sun's, while blue supergiants can be hundreds of thousands of times more luminous. Measuring the luminosity of stars allows astronomers to estimate their sizes, temperatures, and distances. The sun's steady luminosity has provided a stable energy source for Earth throughout the development of life. Earth is not the only world to experience auroras. Jupiter, Saturn, Uranus, and Neptune all have magnetic fields and atmospheres, and when the solar wind interacts with these fields, auroras occur near their poles as well. Jupiter's auroras are particularly intense, powered not only by the solar wind but also by charged particles from its volcanic moon Io. Saturn's auroras change with the seasons, responding to the planet's axial tilt and the Sun's activity. Even Mars, which has only a weak, localized magnetic field, experiences aurora-like glows when solar particles strike its atmosphere. Studying auroras on other planets helps scientists understand the complex interactions between the solar wind, magnetic fields, and atmospheres across the solar system. These glowing displays, whether on Earth or distant worlds, are a direct visible link between the Sun's activity and the planets it illuminates. While a photon leaving the Sun's surface reaches Earth in just over 8 minutes, that photon's journey began much earlier. Energy generated in the Sun's core takes an incredibly long time to reach the surface. Through the radiative zone, photons are absorbed and re-emitted countless times in a random walk toward the surface. This process can take anywhere from 100,000 to 1 million years, depending on the specific path taken. So when you see sunlight, you are witnessing energy that was created in the Sun's core hundreds of thousands of years ago, during the time of early humans on Earth. The light that warms your face today began its journey long before recorded history. This delayed release of energy is part of what makes the Sun so stable, buffering the variations that occur in the core over such long timescales. Without the Sun's gravity, the solar system would not exist. The planets, asteroids, and comets are all held in their orbits by the Sun's immense gravitational pull. This gravity ensures that the solar system remains a stable, organized structure over billions of years. Planets follow predictable elliptical orbits, returning to the same positions relative to the Sun with clockwork precision. This regularity has allowed astronomers to predict celestial events with incredible accuracy, from planetary alignments to eclipses centuries in advance. The Sun's gravity also influences the distribution of material in the solar system, shepherding asteroids into belts and clearing regions through resonances. It is the central anchor, the cosmic fulcrum around which everything else revolves. The order and predictability of the heavens, which inspired early astronomers and continues to captivate us today, is a direct result of the Sun's gravitational dominion. When sunlight is passed through a prism or diffraction grating, it spreads into a rainbow of colors, from red to violet. This spectrum is crossed by thousands of dark lines called absorption lines, each corresponding to a specific element absorbing light at particular wavelengths. By studying these lines, scientists can determine which elements are present in the Sun and in what quantities. This technique, called spectroscopy, revolutionized astronomy in the 19th century, allowing researchers to analyze the composition of distant stars without ever visiting them. The Sun's spectrum contains lines from hydrogen, helium, iron, calcium, sodium, and many other elements. Subtle shifts in these lines can reveal the Sun's rotation, magnetic fields, and motions of plasma in the solar atmosphere. Spectroscopy remains one of the most powerful tools in solar physics, unlocking information encoded in the sun's light. Beyond the 11-year solar cycle, the sun undergoes other periodic changes. Longer cycles, lasting decades or centuries, modulate the strength of the 11-year cycle itself. For example, during the Maunder minimum, a period from 1645 to 1715, sunspot activity was extremely low, and Earth experienced a period of cooler temperatures known as the Little Ice Age. Whether this cooling was caused by reduced solar activity or other factors remains debated. Other cycles, such as the Gleisberg cycle, last about 80 to 90 years. These longer-term variations suggest that the sun's magnetic dynamo is complex, with multiple interacting processes operating on different timescales. Understanding these cycles helps scientists predict future solar activity and its potential impacts on Earth's climate and space weather. The sun, though stable on human timescales, is always changing. Throughout history, the sun has inspired countless myths and legends. In Norse mythology, the sun was personified as the goddess Sol, chased across the sky by a wolf. In Hindu tradition, Surya is the sun god, riding a chariot pulled by 7 horses. Japanese mythology tells of Amaterasu, the sun goddess, whose withdrawal into a cave plunged the world into darkness. These stories reflect humanity's deep awareness of the sun's importance. Ancient peoples recognized that the sun's presence or absence dictated life's rhythms, from the growing of crops to the harshness of winter. The sun was revered, feared, and honored across cultures. Even today, though we understand the sun as a star rather than a deity, it remains a powerful symbol in art, literature, and culture. Our relationship with the sun is both scientific and emotional, rooted in billions of years of life evolving under its light. Every species currently alive on Earth will be long extinct by the time the sun undergoes its dramatic transformation into a red giant. The sun's increasing luminosity will make Earth uninhabitable within 1 billion years or so, long before the sun leaves the main sequence. Even if life manages to persist in some form, perhaps deep underground or in the oceans, the eventual vaporization of Earth's oceans and the scorching of its surface will end all terrestrial life. The sun's transformation is inevitable and final. However, this distant future also offers hope. If humanity survives, we will have billions of years to develop technologies that might allow us to leave Earth, colonize other star systems, or even manipulate the sun itself. While the end of Earth is certain, the potential for life to spread beyond our planet and outlive the sun is a tantalizing possibility that drives both science fiction and serious scientific speculation. Scientists cannot recreate conditions like those in the sun's core on Earth, at least not yet with any permanence. This makes the sun an invaluable natural laboratory for studying physics under extreme conditions. Fusion reactions, plasma dynamics, magnetic field behavior, and fluid dynamics. At temperatures and pressures impossible to achieve, in laboratories can all be observed and studied in the sun. Solar research drives advances in plasma physics, nuclear engineering, and many other fields. Understanding how the sun generates and transports energy informs efforts to develop fusion power on Earth. Studying the Sun's magnetic field helps researchers design better magnetic confinement systems for experimental fusion reactors. In this way, the Sun not only sustains life on Earth, but also teaches us about the fundamental laws of physics that govern the universe. Above the photosphere lies the chromosphere and corona, layers of the Sun's atmosphere that are much less dense than the photosphere. These layers are transparent to most wavelengths of light, which is why they are normally invisible. Only during eclipses, when the bright photosphere is blocked, can we see the faint glow of the chromosphere and corona in visible light. However, these layers emit strongly at other wavelengths, particularly in ultraviolet and X-ray light. Instruments that observe at these wavelengths can see the chromosphere and corona clearly at any time. The corona's transparency allows scientists to study structures and processes occurring high above the Sun's surface, such as coronal loops, prominences, and the acceleration of the solar wind. Understanding these layers is crucial for comprehending space weather and the Sun's influence throughout the solar system. The Sun's magnetic field is central to its behavior. Generated by the motion of electrically conducting plasma in the convective zone, the magnetic field permeates the entire Sun and extends far into space. Sunspots, flares, coronal mass ejections, and many other phenomena are all manifestations of magnetic activity. The Sun's magnetic field is dynamic, constantly changing as magnetic field lines are twisted, stretched, and reconnected. This reconnection releases enormous amounts of stored magnetic energy, powering the most energetic events on the Sun. The study of solar magnetism is a major focus of solar physics. By understanding how the Sun generates and evolves its magnetic field, scientists hope to predict solar activity more accurately, protecting technology and infrastructure from space weather hazards. The solar constant is the amount of solar energy received per unit area at the top of Earth's atmosphere, measured perpendicular to the Sun's rays. It is approximately 1,361 watts per square meter. Despite its name, the solar constant is not truly constant. It varies slightly due to changes in the Sun's activity over the solar cycle, and due to variations in Earth's distance from the Sun as it orbits. However, these variations are small, typically less than 0.1%. Precise measurements of the solar constant are crucial for understanding Earth's energy balance and climate. Satellites continuously monitor the solar constant, tracking how much energy Earth receives from the Sun. This data helps scientists model climate change, solar panel efficiency, and the potential impacts of long-term solar variability on our planet. After leaving the Sun's surface, a photon might travel through space for over 8 minutes before being absorbed by the Earth's atmosphere or surface. But the journey of the energy contained in that photon is far longer. The hydrogen that fused to create that energy may have existed since the Big Bang, traveling through space for billions of years before becoming part of the molecular cloud that formed the Sun. The carbon, oxygen, and other elements in the Sun's composition came from earlier stars that lived and died, scattering their contents across the galaxy. In a sense, every ray of sunlight carries a history spanning the entire age of the universe, a thread connecting the primordial cosmos to the present moment. When you feel the warmth of the sun on your skin, you are touching a legacy that stretches back to the beginning of time. The water cycle on Earth, the continuous movement of water between the oceans, atmosphere, and land, is driven almost entirely by the sun. Solar energy heats the surface of oceans, lakes, and rivers, causing water to evaporate and rise into the atmosphere as water vapor. As the vapor cools at higher altitudes, it condenses into clouds and eventually falls as precipitation, replenishing freshwater sources. The sun also melts snow and ice, contributing to river flows. Without the sun's energy, the water cycle would halt and Earth's water would freeze solid. The availability of liquid water, essential for all known life, depends on the sun's continuous warming. The sun's role in the water cycle demonstrates its pervasive influence on Earth's systems, connecting the atmosphere, oceans, and land in a dynamic, interconnected whole. Thanks to advances in solar physics and computer modeling, scientists can now forecast many aspects of solar activity. They can predict when the solar cycle will reach its maximum and minimum, estimate the likelihood of solar flares and coronal mass ejections, and provide warnings when potentially hazardous solar events are directed toward Earth. These forecasts are not perfect, but they have improved dramatically over the past few decades. Space weather forecasting centers around the world monitor the sun continuously, issuing alerts to satellite operators, power grid managers, and airlines when solar activity poses a threat. As our reliance on technology grows, accurate predictions of the sun's behavior become increasingly important for protecting infrastructure and ensuring safety. The sun, though complex and dynamic, is not entirely unpredictable. Throughout history, the sun has influenced human civilization in countless ways. Agricultural societies depended on the sun's seasonal rhythms to plant and harvest crops. Solar calendars, tracking the sun's apparent motion through the sky, helped organize societies and plan for the future. Eclipses and other solar phenomena were often seen as omens, shaping decisions of kings and empires. In more recent times, the sun's energy has been harnessed through solar panels to generate electricity, providing clean, renewable power. Understanding the sun has also advanced science and technology, from the development of spectroscopy to the pursuit of fusion energy. The sun has been a constant companion, a source of inspiration, fear, worship, and knowledge. It has shaped not only the physical environment of Earth, but also the cultural and intellectual development of humanity. While the sun is an ordinary star in the grand scheme of the galaxy, it is extraordinary to us. It is our star, the one that made life possible, the one that has watched over Earth for 4.6 billion years. No other star will ever hold the same significance. Future generations may travel to distant stars, but the sun will always be home, the light that illuminated the first moments of life's emergence. and nurtured its evolution into the complex biosphere we see today. The sun's light has touched every human who has ever lived, warming their faces, growing their food, lighting their days. It is woven into the fabric of our existence, and even as we explore the cosmos, we carry with us the legacy of the sun, our origin, and for now, our anchor in the vast universe. When ultraviolet B radiation from the sun strikes human skin, it triggers a chemical reaction that produces vitamin D, essential for healthy bones and immune function. This is one of the few ways the human body can naturally generate a vital nutrient. Without adequate sunlight exposure, people can develop vitamin D deficiency, leading to conditions like rickets in children and osteomalacia in adults. Of course, too much UV exposure can also be harmful, causing sunburn and increasing the risk of skin cancer. The relationship between humans and sunlight is one of balance, requiring enough exposure to gain benefits while avoiding excess. This biological connection between the sun and human health is yet another reminder of how deeply intertwined life on Earth is with our star. The rotation of Earth on its axis, combined with the sun's illumination, creates the cycle of day and night that governs life on our planet. As one side of Earth faces the sun, experiencing daylight, the opposite side is plunged into darkness. This daily rhythm has shaped the evolution of nearly all life, influencing sleep patterns, activity cycles, and even genetic expression. Diurnal animals are active during the day, nocturnal animals at night, and crepuscular animals during twilight. Plants open and close their leaves and flowers in response to sunlight. Human societies have structured their lives around this cycle for millennia, waking with the dawn and resting after sunset, though modern artificial lighting has blurred these boundaries. The sun's light defines the most fundamental rhythm of life on Earth, a cycle as old as the planet itself. The sun inspires awe and wonder, not only through scientific discovery, but through sheer beauty. Sunrises and sunsets paint the sky in brilliant hues of orange, pink, and purple. Sunlight filtering through trees creates dappled patterns of light and shadow. Rainbows appear when sunlight refracts through water droplets, splitting into its component colors. The play of sunlight on water, the golden glow of the golden hour, the stark brilliance of a midday sun. All these are expressions of the sun's light interacting with Earth's atmosphere and surface. Artists, poets, and musicians have drawn inspiration from the sun for thousands of years, capturing its beauty in countless works. The sun is not just a physical object, a ball of plasma governed by physics. It is also a source of aesthetic and emotional experience, enriching human life in ways that transcend science. From Earth, no other celestial object can match the sun's brightness. The full moon, though prominent at night, is roughly 400,000 times dimmer. Venus, the brightest planet, is millions of times fainter. Even the brightest stars are insignificant compared to the sun's dazzling light. This brightness is not just a matter of proximity. The sun is intrinsically luminous, generating its own light through fusion, unlike planets and moons, which merely reflect sunlight. The sun's brightness makes it dangerous to look at directly, as the concentrated energy can damage the retina. Yet, it is this same brightness that illuminates our world, making vision possible and sustaining the intricate ecosystems that depend on light. The sun's dominance of our sky is absolute and essential. While light is the most obvious form of energy the sun sends to Earth, its influence extends far beyond the visible spectrum. The solar wind, magnetic fields, and high-energy particles all affect Earth's magnetosphere, ionosphere, and upper atmosphere. These interactions create phenomena like auroras, but they also have practical consequences. They affect radio communication, GPS accuracy, and the orbits of satellites. They can induce currents in power grids, potentially causing blackouts. The sun's influence shapes the environment of near-Earth space, a region increasingly important as human activity expands beyond the atmosphere. Understanding these connections between the sun and Earth is essential for managing the challenges of the space age, protecting technology, and ensuring the safety of astronauts. If humanity were to disappear tomorrow, the sun would continue to shine, indifferent to our absence. It has existed for billions of years before us and will exist for billions more after we are gone. The sun's story is far longer than humanity's story, yet, in a strange way, the sun is our story too. We are made of elements forged in stars. Our entire existence, every thought, every feeling, every achievement has been powered by the sun's energy. We are children of the sun, born from its light. Even if we vanish, the sun will remain, a testament to the grand processes that govern the universe, shining steadily in the void, waiting, perhaps, for the next spark of life to emerge under its warmth. Finally, we return to where we began. The sun is a star, one of hundreds of billions in the Milky Way galaxy, which is itself one of hundreds of billions of galaxies in the observable universe. In the grand cosmic scheme, the sun is unremarkable, a medium-sized middle-aged star in a typical galaxy. Yet to us, it is everything. It is the source of life, light, and warmth. It has shaped the evolution of every organism on Earth. It has inspired wonder, curiosity, and countless questions about our place in the universe. The sun is both ordinary and extraordinary, a single point of light in the vast cosmos and the center of our entire world. As we drift off to sleep, let us hold this thought. We are connected to the universe through the sun, a living bridge between Earth and the stars, a light that has burned for billions of years and will burn for billions more, quietly sustaining the miracle of life in the endless expanse of space. Good night.